Hello, my name is Evan Acosta. This is my Lab 2 video report on the observation of an object in projectile motion. So first, we're going to go through a quick introduction and purpose. The overall goal of this lab was to observe the motion of an object as a projectile. In this scenario, I used a paper ball. I then put a video of the paper ball moving into Tracker and basically analyze how it worked and how it moved. Then I created a computational model for both the ball without air drag and with air drag. Afterwards, I compared the data from all three models and then drew my conclusions. The purpose of the lab basically is just to utilize Newton's second law as well as the kinematic equations to see how a projectile behaves in real life. Here are some fundamental principles that I used during the lab. So the first one is Newton's second law. It describes the relationship between F net and the mass and acceleration of an object. And basically, you can derive the kinematic equations from this, which allow you to determine the velocity, position, and the acceleration of a given object at a given time. And then there's just the concept of projectile motion, which, as you can see by this little example right here, is basically just an object being thrown in an arc. Um, and then it usually in the real world has non-constant of forces being applied, like the force of drag, the force of gravity. Here is a screenshot of my tracker. As you can see, this before and after picture. I can go and show you guys the video. So as you can see, it tracks the paper ball all the way down. Right? And then here is a quick screenshot of my code, which basically just utilized the kinematic equations as well as like the the gravitational force equation and the air drag equation to um, basically just create a model of the ball, which I can do right now. So I was playing around with the values, so it's not quite the same as my the data from my from my actual lab, but as you can see, it basically creates a quick computational model and it's got all of the graphs for x versus time, y versus time, and that sort of thing. All right. Here's the observations for my tracker. I was able to calculate a rough estimates of both velocities. This one traveled roughly 0 0.8 meters in 0.533 seconds. I was able to plug into the kinematic equations, which gave me a value of about 2.4 meters per second. In the y direction was a similar case. I just used the kinematic equation until it hit the peak to find the positive y velocity that it started with. Here's my calculations for those two. And then here's a comparison between the observed and predicted motion of the lab. So the orange line is the glow square model without air drag. As you can see, the x direction is constant because there's no force acting in the x direction. The green is the glow square with air drag, which as you can see for the x direction, slowly it is decreasing because the drag is working against the motion in the x direction. And blue is the experimental data. As you can see, they're actually quite different. I think this is partially because I had a lot of trouble getting the coefficient for the air drag. I kind of just plugged in numbers until I was able to get a graph that looked relatively similar. But there's a lot of factors that aren't taken into account that exist in the real world in my computational model. So what does this all mean? It is relatively accurate, the computation model, but it does leave out a large amount of variables. So one of these, an example of one of these is the force of my hand on the ball. As it leaves my hand, the force could be applied in different locations. My paper ball isn't exactly perfectly spherical. It's got edges and ways that the air can be trapped around it. Um, and like other external factors that may have acted upon the paper ball, such as, um, just like maybe even the air conditioning in my room or a fan blowing on it could have also affected it. The ball did not have enough time to reach the terminal velocity. All the graphs show the ball continuing to speed up in the negative y direction. So um, obviously none of the models were able to predict a terminal velocity. In order to find one or create an experiment where I could find one, I could drop the ball from a higher location such that it had enough time to reach the terminal velocity. I could also just turn up the time in the glow script problem or the glow script computation model. So what if the object were to be thrown straight up at the same speed? If it was thrown up with the same amount of speed in the y direction, it would take the same amount of time to hit the ground as if it was thrown, like in the original experiment, because the speed in the y direction is the same for both experiments. The positions, velocities, and acceleration due to gravity are all the same, so there's no difference. All right, my name is Evan Acosta. Thank you for watching my Lab 2 video report.